Welcome to part 2 of the product architecture video. Make sure to watch video 1 before proceeding with this one. In this video, I'll talk about the 4 main steps of establishing a product architecture. We're using the same case study, which was Hewlett-Packard inkjet printer. The home printing division of HP needed to expand product variety while cutting manufacturing costs. Inkjet technology has helped consumer and small office markets by providing high quality, affordable printing, but now as the competition was growing, to keep this product successful, they needed to tailor some printers to specific markets' demand. So redesigning them with the specific market demands in mind, while reducing production expenses. So that's the reason behind this case study. So we'll see some examples in this video for this case study. The 4 main phases of establishing product architecture are schematic, cluster, layout, and interactions. Those are the keywords that I come up with to help you kind of remember them. The first step is to create a schematic of the product. I'll talk about it in a minute, what it means. Then you cluster the elements of schematics into chunks. Then you create a rough geometric layout of the product, whether it could be on paper or it could be a physical rough geometric layout. And lastly, you identify the interactions between the chunks and between the functions. And those could mean incidental or fundamental interactions. And we'll talk about what those mean. So let's just start by schematic. Schematic is a diagram that represents teams' understanding of the constituent elements of the product. A schematic for DeskJet is shown here. At the end of concept development phase, some of the elements in a schematic are physical concepts, such as front-in, front-out paper path. Some of the elements correspond to critical components, such as the print cartridge the team expects to use. On the other hand, some of the elements remain described only functionally at this stage. So this is a mixture of physical concepts and functional concepts. These are the functional elements of the product that have not yet been reduced to physical concepts or component. For example, display status is a functional element required for the printer, but the team hasn't designed or decided what that means and what it's going to be done. So this is the difference between a schematic and function diagram. In function diagram, everything you see there is a function. Now, some of those have been kind of designed or reduced to physical concepts in this schematic diagram. So the elements that have been reduced to physical concepts or components are usually the ones that are central or critical to the basic product concept. Anything that's not reduced to physical concepts and that they still remain as unspecified and in terms of function, they're usually subsidiary functions of the product. So at this stage, any main function should be reduced to physical concepts or physical components. The schematic should reflect team's best understanding of the state of the product, but it doesn't have to have every detail included in it. A good rule of thumb is to aim for fewer than 30 elements in the schematic for this purpose, which is establishing the product architecture. Step 2 is assign each element to a chunk. The keyword for it was cluster. The challenge of step 2 is to assign each of the elements in the schematic, step 1, to a chunk. One possible assignment of elements to chunk is shown here for the DeskJet printer, where there are 9 chunks used. There are several other viable alternatives, and one extreme, each element could be assigned its own chunk, and it will yield 15 chunks. Okay, that's one end of extreme spectrum on options. Each element, one chunk. One chunk. And the other extreme example, the team could decide that the product would have only one major chunk and then attempt to physically integrate all of the elements into one product. So on the other extreme is one chunk. All of the elements, all elements will turn into one chunk. So in this schematic, we're at 9 chunks. So we're kind of in between. We're kind of somewhere here, not any of the extremes. So again, depends on the team, depends on design capabilities, depends on the product, depends on the decision between modular versus integrated architecture, and the factors that we talked about in video 1. Next is to create a rough geometric layout. A geometric layout can be created in 2-dimensional or 3-dimensional. It could be drawings, computer models, or physical models made out of cardboard or foam, for example. This image here shows geometric layout of the DeskJet printer, showing the major chunks. Creating a geometric layout forces the team to consider whether the geometric interfaces among the chunks are feasible, and to work how the basic dimensional relationship among the chunks exists. For example, here, by considering cross-section of the printer, the team realized that there was a fundamental trade-off between how much paper they can store in the printer and the height of the machine overall. So the amount of paper based on this geometric layout would directly affect the overall dimension of the printer. And lastly, step 4 was figure out the interactions. And as we talked about, there are fundamental interactions and incidental interactions. Most likely a different person or different team will be assigned to design each chunk, because the chunks interact with one another in both planned and unplanned way. These different groups will have to coordinate their activities and exchange information with each other. To better manage this coordination process, the team should identify the known interactions between chunks during the system level design phase. For the fundamental interactions that we talked about, or we will talk about, are those that correspond to the lines on the schematic that connect the chunks to one another. For example, a sheet of paper flows from the paper tray to printer mechanism. Paper tray to printer mechanism. That line that connects the two, that's a fundamental interaction. That line right there is a fundamental interaction. This interaction is planned, and it should be well understood from very early schematics of the architecture. It's fundamental to the system's operation, and that's why they're called fundamental interactions. These are easy to deal with. They're known, they're planned. Second type of interactions are incidental interactions. These are the interactions that arise because of the particular physical implementation of the functional elements, or because of the geometric arrangement of the chunks. For example, here, this vibration here, introduced by the actuators in the paper tray, could interfere with the precise location of the printer cartridge in the x-axis, or precise printing. For a small number of interacting chunks, if you have less than 10, in this case there were 9, an interaction graph is a convenient way to present the incidental interactions, and this is what we have here, which is one possible interaction graph for the DeskJet printer. For larger system, this graph could become confusing. An interaction matrix is as useful tool that could be used instead, that can display both fundamental and incidental interactions. So we can use the mapping of the interactions between the chunks, whether it's an interaction map, interaction graph, or interaction matrix. We can use it to provide guidance for structuring and managing the remaining development activities of the project. Chunks with important interactions should be designed by groups with a stronger communication and a stronger coordination between them. 4-step method for establishing product architecture that we talked about guides the early system level design activities. But many more detailed activities remain for the project. Here we discuss some of the issues that frequently arise during subsequent system level design activities and their implications for product architecture. First one is secondary systems. Secondary systems like safety or power systems are additional elements that are not shown in initial schematic and are developed as system level design evolves. These systems often span multiple chunks, typically involving flexible connections or wiring or tubing, and systems such as those ones, that they should not be overlooked. The responsibility of designing secondary systems could be assigned to a specific individual or specific teams, but that creates a management challenge when components cross the chunk boundaries and move into other chunks of architecture and schematic. The second one is establishing the architecture of chunks themselves. Each chunk in a complex product can be a system with its own architecture, containing numerous parts or subfunctions. Careful architectural planning is crucial at both product level and chunk level to ensure that functionality and integration within the large system is implemented. For example, the architecture of a print cartridge may involve various configurations such as independently replaceable ink reservoir and something like that. And lastly is creating detailed interface specifications. As design progresses, integration between chunks become more defined, detailing signal flows, material flows, and energy transfers. These interfaces often formalize in specifications as such as contract between chunks that ensures proper coordination and integration of components. Detailed interface specification clarifies the interactions, such as connection between a printer cartridge and a logic board in a printer. So these are some of the issues that should be taken care of during system level design and not forgotten about them during the design of the product. Thank you very much.